dear students, now you are comfortable with the term gravitational field intensity. In this session, I am going to discuss in detail gravitational field intensity due to Earth, which is known as acceleration due to gravity. We will see how this varies with height, with depth, or with rotation of Earth, or even due to shape of Earth. So let us see these all things in detail, and then we will solve some questions also to clarify our concept. So let's get started. In the last session, we were discussing about gravitational field intensity, and now we are going to see what is acceleration due to gravity, because we had seen that gravitational field intensity is dimensionally equal to an acceleration term. So now it can be said as acceleration due to gravity. What will be its value at the Earth's surface? Whenever a force acts on a body, it produces acceleration. So when a body falls freely towards the Earth under the effect of gravitational pull, its velocity changes with time, which produces acceleration. Therefore, acceleration produced in the motion of a body under the effect of gravity is called acceleration due to gravity. And as Earth may be considered as a large sphere made of a large number of concentric spherical shells, with the smallest one at the center and the largest one at its surface, any particle kept at a point outside the Earth is obviously outside all the shells. Thus, all the shells exert a gravitational force at that particle such that their masses are concentrated at their common center. So, if we suppose that a particle moves inside the Earth and sphere, let us consider there is a point at the surface of Earth where r is radius of Earth and m being its mass, then that gravitational pull at the surface can be written as Gm upon r square, because the Earth will behave for the point which is at its surface as it is a particle mass which is situated at the center of Earth, and we can write gravitational pull by Gm1 m2 upon r square. This should be equal to mass of the body multiplied with acceleration due to gravity. So from here we can write value of acceleration due to gravity that is at the surface of Earth, and its value is equal to Gm by r square, where m is mass of Earth and r is radius of Earth. If I substitute all the numerical values, then G comes out to be nearly equal to 9.8 meter per second square. Now onwards we can use this as almost a constant if the object is at the surface of Earth, and can take value of G in any numerical whenever it is required. Now let us see one numerical based on this. What will be the relation between the acceleration due to gravity on the surface of Earth and on a planet respectively, whose mass and radius are twice that of the Earth? Here we have to check acceleration due to gravity at the planet with respect to Earth. So let us consider that G be the acceleration due to gravity at that planet. So its value should be equal to gravitational constant multiplied with mass of planet upon square of radius of planet. And since it is given that mass and radius both are twice, so it can be written as G into twice the mass of Earth upon 4 times square of radius of Earth. And since we know that this Gme upon re square can be written as small g, so we can write this value to be G by 2. Acceleration due to gravity on that planet is half of that due to on the Earth. One more question I have. A spherical planet far out in space has a mass m0 and diameter d0. A particle of mass m is falling freely near its surface. What will be the acceleration of that particle? Let us now consider acceleration of that particle to be equal to Gp. So it can be written as G mass of planet upon square of radius of the planet. But here, since mass of planet is equal to m0 and radius of planet is equal to d0 upon 2, where d0 is diameter of that planet. So if I substitute the values here, Gp will be gm0 upon d0 by 2 and then square of this. That will give 4gm0 upon d0 square. This is the value of acceleration of the particle. So now we know about what is value of acceleration due to gravity at the surface of Earth and how it can be calculated at surface of different planets if we know mass and radius of that planet. But let us see what happens to this acceleration due to gravity when we go above the surface of Earth or if we go inside the surface of Earth. So let us see, is there any variation in value of g? The first I am going to consider is variation in g with height. For this, let us consider a particle of mass m which is at a height h from the surface of Earth. Obviously, radius of Earth is Re and mass is Me. Now, if we write gravitational pull on that particle mass, it can be written as g mass of Earth into mass of that particle upon distance of the particle from center of Earth, which as you can see here can be written as Re plus h and its square. So this is the force. Of course, it can be equated with mass into acceleration due to gravity. Now we have to check whether this acceleration due to gravity has some different value. So let us denote this by g dashed. From here now m got cancelled and we got value of g dash to be equal to gme upon Re plus h whole square. Now if I take Re outside the bracket, it can be written as gme upon square of Re and then this is 1 plus h by Re whole square. This term can be written as small g, which is value of acceleration due to gravity at the surface of Earth, and this should be multiplied with 1 plus h by Re to the power minus 2. So it is the general expression for acceleration due to gravity at a height h above the surface of Earth. But if we consider that this height is small, if it is small with respect to radius of Earth, I am considering a special case. If h is very small as compared to Re, then this g dashed can be written as, with help of binomial expansion, we can now write this value to be 1 minus 2h by Re. So this is variation of acceleration due to gravity with height if the height is small as compared to radius of Earth. Otherwise, if height is not small, it is a large one, then we have to use this general result which can be used for any height. Now let us see how the value of g dash is calculated with height. I have one example. At what altitude the acceleration due to gravity reduces to half of its value as that on the surface of the Earth. Take radius of Earth as 6.4 into 10 to the power 6 meter and g on surface of Earth to be 9.8 meter per second square. Let us write our general relation for acceleration due to gravity at a height h from the surface of Earth. It can be written as g dashed is equal to g 1 plus h by Re to the power minus 2. But it is given in question that g dashed has to be half of g. So if I write this to be equal to g by 2, that is g upon 1 plus h by Re whole square. These two got cancelled. From here I can write 1 plus h by Re to the power whole square to be equal to 2. And on taking root, it will be 1 plus h by Re is equal to root 2. From here we got h is equal to root 2 minus 1 multiplied with RE. On substituting the numerical value, this will come out to be 2.65 into 10 to the power 6 meter. As you can see here that I had used the general expression because since g has become half of the value on earth, it cannot be at a small height, it has to be at a large height, which you can see we obtained in answer also. Now let us see one more example. At what height the acceleration due to gravity decreases by 36% of its value on the surface of earth? Here the decrement is given as percentage. So again if I write g dash to be equal to g upon 1 plus h by re whole square, then g dash can be written as g minus 36% of gv, so it has to be 0.36 g. That is equal to 0.64 g. If I substitute here, it will come out to be 0.64 g is equal to g upon 1 plus h by re whole square. These two got cancelled and we got 1 plus h upon re to be equal to 1 by root under 0.64, that is equal to 1 upon 0.8, which is 10 by 8. So we got value of h to be equal to 5 by 4 minus 1 times re, which is 1 by 4 times re. This is our final answer. Now I am going to discuss how acceleration due to gravity changes if we go inside the earth. We can consider case of a mine, or if a tunnel is dug inside the earth, what will be the value of acceleration due to gravity inside. Let us consider a point which is inside the earth at a depth d. Now from the center of earth, this distance will be equal to re minus d. As we know that if p is the point where we have to calculate value of acceleration due to gravity, then we can assume that this earth is made up of a number of spherical shells, and all the shells which have radii more than re minus d will have no contribution towards field intensity at a point which is inside them. So only we have to consider field due to the part of earth which is having radius up to re minus d. And if I write mass of that smaller part of earth, it can be written as 4 by 3 pi re minus d whole cube multiplied with density of earth, and density of earth can be written as mass of earth upon its volume, which is 4 by 3 pi re cube. These terms got cancelled and we got value to be equal to me upon re cube multiplied with re minus d whole cube. This is the mass which will have an effect of acceleration due to gravity at the point P, that is a distance d inside the surface of earth. And now we can write acceleration due to gravity g dash to be equal to g mass of this smaller part upon its distance has to be re minus d whole square. On substituting the value of ms, we will get g upon re minus d whole square, and then value of ms is me re minus d whole cube upon re cube. 2 of the power got cancelled and the result is g me re minus d upon re cube. Now we know that g me upon re square can be written as small g. So it is small g 1 minus d by re. This is how acceleration due to gravity decreases with depth inside the earth. You can see this rate of decrement is half of that of the rate of decrement which we had got when it is calculated at a height h above the surface of earth. So here decrement is at half of the rate. Now based on this result, again let us see one example. At what depth the acceleration due to gravity becomes 0? As just now we have obtained the result, g dashed can be written as g 1 minus d by re. So for g dash to be equal to 0, d should be equal to re. Depth should be equal to radius of earth. What does this mean? That it has to be at the center of earth. So we can say that there is no acceleration in a body when it is at the center of the earth. From here we can even draw a graph also that shows variation of g with r. As its value is 0 at the center of earth, so it will pass through origin, will increase linearly and will be maximum at its surface when r is equal to re, and its value at this point is equal to 9.8. G dash here is equal to value of g, and after that it starts decreasing as 1 by r square. So this is variation of g dash with respect to r, where r is position of point from the center of earth. One more example I have. At what depth from the surface of earth the acceleration due to gravity will be 1 by 4th the value of g on the surface of earth. Again we can use the same relation, g dash to be equal to g 1 minus d by re. Here it is given that g dashed is g by 4, so it has to be g by 4 is equal to g 1 minus d by re. These two got cancelled, and on solving we will get d by re to be equal to 3 by 4. That gives d is equal to 3 by 4 of re, which is 0.75 re. So at this much of depth, the acceleration due to gravity becomes 1 by 4 of its value on the earth. Now we have to consider one more kind of variation in g, that is due to the shape of earth, because for practical purposes we consider that earth is having a spherical shape, which is not true. The earth has a somewhat elliptical shape. So at the pole this diameter is less than the diameter at equator. If I write radius for pole to be equal to rp and at equator this be re, we can say that the value of rp is less than that of re. So it has somewhat oval shape. This value re, exactly if it is measured, is equal to rp plus 21 kilometer. As this is very small value as compared to radius of earth, so generally we neglect this oval shape. But of course g does vary due to this shape also, as we know that g is proportional to 1 by r square. So of course its value will be maximum at the pole and minimum at the equator, and from here we got gp to be greater than ge. One more variation we can consider for g, that is due to rotation of earth. So let us consider rotation of earth. Here I am taking one particle p which is at angular distance theta from the equator. Radius of earth we know is r. Now with rotation of earth, this particle will move in a circle for which radius can be written as, I have denoted the distance by small r. This angle theta, that is with the equator of earth, is known as latitude. This angle is called latitude. Now if we consider angular speed of earth to be equal to omega square, so what forces will be there on the particle? The forces will be, now here I am drawing separately the forces. One force has to be mg, that should be towards the center of earth. If we consider with respect to Earth, then of course it is a non-inertial frame. So one pseudo force we have to write, and its value should be equal to 𝕝²r, where r is radius of path for this particular particle P, and its resultant will be actually the net force mg dash. So from here we can write mg dash can be written as, it will be mg square plus 𝕝²r square of this plus 2 mg 𝕝²r cos of, what is angle between these two now? This angle can be written as pi minus theta. So if I substitute this value pi minus theta here, the resultant force will be equal to mg whole square plus 𝕝²r whole square minus 2 mg 𝕝²r cos theta. And then we can write g dash to be under root g square plus 𝕝² square minus 2g r 𝕝² cos theta. This is the value of variation in g with rotation of Earth. Now it all depends on the latitude of that particular point. So if we consider a point which is at pole, this theta will be equal to 90 degree, and this term here vanishes, and we can write at pole the value will be equal to g dashed will be, this is only g square plus, if the point is at pole, then even this r also will reduce to 0. So the value is exactly equal to g. But what about the point if it is taken at equator? Then we can write g dash at equator to be equal to g minus r 𝕝² cos square theta. As small r also can be written as capital R cos theta. So we got final value at equator of Earth to be equal to g minus 𝕝²r cos square theta. From here also you can see that acceleration due to gravity at pole is more than acceleration due to gravity at equator. Let us consider few more examples. The value of acceleration due to gravity at a depth d is 1/3 of its value on the Earth's surface. Find the value of d. Now we know that with depth, value of g dashed is equal to g1 minus d by r. And since this g dashed is given as g by 3, so it will be g by 3 is equal to g1 minus d by r. These two got cancelled, and we will get finally d to be equal to 2r by 3. At this depth, acceleration due to gravity will be 1/3 of its value on the Earth's surface. One more example I have. Find the percentage change in acceleration due to gravity when a small body is taken to first to an altitude of r by 100 and then at a depth of r by 100. Let us first write at height. So we can write g dash to be equal to g1 minus 2h by r. Here I have taken the approximate result because altitude is 100 times that of r, which is very small as compared to r. So we can write directly g dash to be equal to g1 minus 2h by r. In this question it is asking for percentage change. So then we can write delta g by g into 100. That has to be the percentage change in value of g, and it can be taken as minus 2h by r into r by 100 into 100%. This value, if you calculate, it will be equal to minus 2%. So acceleration due to gravity will decrease by 2% if we go an altitude of r by 100. In next part it is asking for the depth. Let us consider the formula for depth. It has to be g dash is equal to g1 minus d by r. From here we can write delta g by g into 100 to be equal to minus d by r into 100. Now this D is equal to R by 100. Now D itself is R by 100, so it will be minus R by 100 R into 100. That gives the decrement to be minus 1%. With this, our today's session is complete. I hope you understood everything and enjoyed today's class. Let us wait for the next class. Till then, keep practicing and do take a good care of yourself. Goodbye.